speaking of masses, take a look at the penny and take a look at this supertanker. You see the penny? Now take a look at this supertanker. We've got the supertanker. All right, penny is obviously, you know what a penny feels like in your pocket. Let's talk about the supertanker. All right, let's do some mind games. This one is going to be cute. All right, so we'll be doing a bit of a mind twister thing. All right, this supertanker, I'm looking at the number. This is 150 million kilograms. That's 330 million pounds, guys. That's 330 million pounds. 330 million pounds. This is going to be heavier than most of the buildings. This is going to be heavier than your home. This is going to be heavier than one of the biggest buildings at school. This thing's heavy. So 330 million pounds, which means that this thing is incredibly heavy. All right. So it's in water, and it's super, super, super heavy because it's a super tanker. So I'm going to give you a rope to tug on. So the rope is going to be tied to the super tanker, and I'm going to ask you to tug on it as hard as possible. When you tug on it, do you think you're going to be able to move the super tanker by tugging on it? Yes or no? The answer to that question is, what do you guys think? Do you think it's going to move when you tug on it?
No.
Okay, but most of you guys will say no. You're not going to be able to make it move. It's not going to move. This thing is heavy. It doesn't matter that it's in water. It's not going to move. All right? It doesn't matter how hard you tug on it. It's not going to move. It's not going to budge. No way it's not going to move. Why not? It's not going to move because it is heavy. Not only is it heavy, it's super, super, super heavy. It's not going to move. It's not going to move. It's that heavy. But what if I make it weightless? How do I do that? Well, it's simple, guys. Here's my plan. I want to take it out into deep space. When you take it out into deep space, it's going to become 100% weightless. It's going to become 100% weightless. This thing is going to weigh less than a penny in your pocket. Got it? So this thing in deep space is weightless. This thing is going to weigh less than a penny. Yeah, it is huge. Do you get it? It's huge. I get it. It's huge, but it's weightless. It's got paperweight. It weighs less than a paper. It weighs less than a penny. So the size doesn't matter. I'm going to construct a platform out of metal for you, and I'm going to give you some magnetic shoes so you got your footing. Now that you have your footing, I'm going to give you the same rope to tug on. Will it move now when you tug on it? Yes or no?
I think no.
How much does it weigh?
Nothing.
It
But
weighs
it's
nothing, right? So can you move a penny? Yes or no?
yeah.
You don't have a problem, right? So if something weighs less than a penny, your initial thought is, oh, it's going to move fine, right? But your second thought is, wait a minute, something is off here, right? So what is it that you're seeing that most of us are not seeing that makes it disagreeable?
So just because the weight's nothing, the inertia is still there. The mass is still there. The resistance to change in motion is still there.
So Jack, you're thinking that that's probably weight. Yeah, it is weightless, but you're thinking that it may not move despite the weight? Because I can tell you what most people are thinking. If it's weightless, it's going to move regardless, especially in space. All right, so let's investigate. A lot of you guys are thinking, wait a minute, you can move it here on Earth while it was in water because it weighs more than the buildings where you work, for God's sake, and now it's weightless. It weighs less than a penny, and you know you have no problem just moving a penny around. It's in your pocket. You just grab it, you flip it, you can do whatever you want with it. It's huge, but you're thinking it's like paperweight. Who cares, right? All right, so just because something is weightless doesn't mean that you can actually move it. You're thinking, oh, here's my opportunity to play Hulk in reality, right? You grab the rope, you tug on it, and then you grab it, you spin around, and then you just let it go. You let it fly, right? You get to play Hulk. You can capture it on video, put it on TikTok, Facebook. You'll get a lot of likes. Life is good. So that's what you guys are thinking. If that line of reasoning is correct, then look what happens. Those of you guys who are a little bit confused about what's going on, it's kind of weird when it comes to weight and mass. Because of the way we express mass in terms of its weight, in terms of the object's weight, you guys have this very strong correlation between what mass is and what weight is. And you have a way of defining what mass is in the way how much something weighs. In reality, you know the answer when I ask you a really simple question like, hey, which one is heavier? You've just seen the experiment. And then you go, oh, the one on the left is heavier. And then I say, which one is more massive? You will say the one on the left is more massive. Okay? Because against the same external force, this one was able to persist longer. All right, this one had a larger tendency to keep on rolling. Your mind makes these computations real fast without you noticing. But at the same time, your mind is a prisoner of your knowledge. As far as your knowledge is concerned, mass and weight are correlated. Okay, weight defines how much mass you have. And that's, you make that correlation because of the simple reason that we have a tendency to express everything, every single mass by its weight in the United States. And that's the reason why you guys aren't able to separate yourselves. When I make something weightless and all of a sudden you go, wait a minute, I should be able to move it around because that's what your mind says. All of a sudden I was able to trick you into thinking something which is not true.
When it comes
So here's what I want you to do. We are going to be watching this tiny little clip and look at the way I will describe something and listen to it carefully because you will find the answer in my
to
explanation.
destruction, no plane has ever been totaled in a crash test more thoroughly than this one.
I will repeat what this guy is saying, except I'm going to repeat it differently.
An F-4 Phantom sent hurtling along a 2,000-foot sled track at 480 miles per hour.
All right, this thing is moving at 480 miles per hour. All right, so that's its speed.
The 43,000 pound
It's got 43,000 pounds. Okay, 43,000 pounds to you guys, it represents its weight. To me, it doesn't represent its weight. To me, it represents its inertia. It's got a 43,000 pounds of mass that says, it's got a 43,000 pounds of tendency that says, I'm going to keep on moving at 480 miles per hour. All right, it's tendency to keep on moving at that speed. It's got a 4,300 pounds of tendency to keep on moving in that direction. What that means is if I were to stand in front of this, it would go right through me. All right, so it's got such a large tendency, it would not even acknowledge my presence. Except the problem is now it's going to be going up against the block, which is 1 million pounds.
plane literally dematerialized as it plowed into a 1 million pound, 12-foot thick.
You're thinking, oh, that thing is heavy. It's 1 million pounds. Well, that's not what it says at all. It says it's got a 1 million pounds of tendency to retain its initial motion. What that means is it's not moving, so it's not gonna want to move. It's got a 1 million pounds of tendency that says, hey, I'm gonna resist in change of motion. I'm gonna resist to change of motion, which means that I'm not gonna want to move. It's got 1 million pounds of tendency that says, I'm not moving unless you can make me. And this has got a 43,000 pounds of tendency that says, hey, I'm gonna keep on moving regardless of what you're doing. So what happens?
Concrete wall, leaving behind nothing but dust and rubble. The test,
Now watch the airplane.
commissioned by the Japanese,
All right, so watch the center of mass. Okay, here's what the center of mass is. I want you to just gauge its acceleration.
was designed to see if the
You notice that it keeps on moving at a constant speed in a straight line
concrete casing that houses
to complete oblivion. Because this darn thing is just so incredibly massive. It's got 43,000 pounds. That says, I'm going to keep on moving, and it keeps on moving into oblivion. And look at the 1 million pound block.
nuclear power plants would stand up
It's not budging.
to a direct hit by a
All right, both of them are real massive, and they do exactly what mass is supposed to do. Mass gives you that tendency. One of them has a really large tendency to keep on moving into oblivion.
falling jet.
The other has a very large tendency not to move, and it's not moving. It's not because they're heavy. It has nothing to do with it, but because they're extremely massive.
Though the jet disintegrated, damage to the concrete wall.
Have you ever experienced something like this within your own lifetimes? Okay, I'm guessing that most of you guys are late teens, early 20s. So yeah, you have experienced something like this, but you were very little at the time if you were born at all.
Was mine.
That was like 19 years ago, guys, 9/11. I'm not talking about the Twin Towers getting it. I'm talking about Pentagon getting it. And a lot of conspiracy theories are, where's the evidence that the Pentagon got hit?
Not all crash
Well, Pentagon was protected just like
tests
that.
take place on the road
Notice that not much left behind.
or in the sky.
You see, here's a small plastic boat moving along at 2 miles per hour. As you can see, I was able to stop the boat with just my hand. Now we see a big ship in a harbor, coasting at about the same 2 miles an hour.
That's a big boat!
Now, not only could I not stop it with my hand, a pier doesn't even stop it.
Whoa, look out!
So you mean the something has, the more inertia it has, right?
Hey, you got that one, that's right. Something with a lot of mass might be hard to start moving, but once it starts, it will be hard to stop.
All right, so this brings us to the next point. It's the movie Armageddon.
This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide changed all that. It hit with the force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just a question of when.
right, so for those of you guys who've seen the movie Armageddon, give yourselves 5 points. The premise of the movie is we have an asteroid the size of Texas coming towards us at about 25,000 miles per hour. It's on a collision trajectory. All right, so remember, guys, this is the size of Texas, but it's coming from deep space. It's weightless. It's 100% weightless. It weighs less than a penny. Due to the fact that it's weightless, why not just send out a bunch of astronauts and give them some jetpacks, and then have these astronauts just push this asteroid from its free collision trajectory so that it misses Earth as opposed to just colliding with it. If you can move a supertanker around because it's weightless in space, if you go by that logic, you could do the same thing using this asteroid. You could do the same thing with this asteroid, guys. You're thinking, wait a minute, that supertanker was motionless. It wasn't moving until you started to move it around by using your rope. This thing is coming at you at 25,000 miles per hour, so that means something. What does it mean? It doesn't mean anything. So it's coming at you at 25,000 miles per hour. It's weightless. All right? And something moving much faster than that, light, it moves at the light speed. It's weightless. When it hits you, you don't bounce around. This thing weighs as much as the light does. So why not just send someone out, give this person a jetpack, and have this person just push it out of the way so it doesn't collide with the Earth? Why not do that one?
Proximity of the asteroid and no prep time, none of our primary plans can work.
Why don't we just send up 150 nuclear warheads and blast that rock apart? Terrible idea. Was I talking to you?
This is Dr. Raul Quincy from research, pretty much the smartest man on the planet. You might want to listen to him.
General, if you consider your target, composition, dimensions, sheer velocity, you could fire every nuke you've got at her and she'll just smile at you and keep on coming. You should know that the president's scientific advice.
All right, so what that means is this thing is so darn massive, it's gonna keep on moving in a straight line at a constant speed, guys. It's so incredibly massive. There's nothing that you could do to stop it, in essence. Something the size of Texas is an extremely large inertia. Just because something is weightless doesn't mean that it's massless. Remember, guys, that mass is the measure of inertia. Bigger the number is, bigger the inertia is.
Just think that a nuclear
Bigger the mass is, the bigger the tendency is.
blast that changed this asteroid's trajectory. I know the president's chief scientific advisor. We were at MIT together. And in a situation like this, you really don't want to take the advice from a man who got C- in astrophysics. The president's advisors are wrong. I'm right.
Hitting the rock from the outside won't do the job.
Imagine a firecracker in the palm of your hand. You set it off. What happens? Burn your hand, right? You close your fist around the same firecracker and set it off. Your wife's could be opening a ketchup bottles the rest of your life. You suggested that we blow this thing up from the inside. That's exactly what I'm saying. How?
We drill.
All right, so they decided to actually break it down, which means that they decided that they're going to reduce the size of the mass, trying to make it much more manageable. So that's the direction that they decided to go. Just because something is weightless doesn't mean that it's massless. Jack, you yourself 20 points for the comments that you made. In space, the supertanker is going to be weightless, but nonetheless, it's still extremely massive. That's still 330 million pounds of mass. Remember what happened to a million pound of block? It didn't move because it had a tendency not to move when it was struck by an airplane. And now imagine that tendency to be 330 million pounds. So it's going to be 333 times larger than a million pounds. So that thing is not going to move in space either, guys. So that tendency is known as mass.